All right. Hello, everybody. Thank you for coming out to our second session for beginner track. Today, we're going to be teaching you about dynamic programming, which is a pretty powerful technique that will help you optimize your code. So today, the link to the slides is right here. And here's the portal code. Okay. So before we begin, just a quick note on some things. So we're writing editorials for our contests, and the one for last week will be up very soon on our GitHub repository. And also, you get participation points for unmuting your video and audio, and people with the most participation points will be entered to a raffle at the end of the quarter. We also have office hours weekly every Monday from 6 to 8 p.m. Pacific time. And lastly, you can use our Discord channel to discuss problems or anything with fellow attendees and officers. And yeah, so you can get these links from the slides. Wait, can someone maybe put the link to the slides in the chat if you haven't yet? Okay, so quickly before we begin, for our contest problems, we're using Caddis. So for this, you need a Caddis account. So if you haven't registered an account yet, please go to this link and register an account so you can do the problems and submit your solutions to our online judge. And also tell us your username so that we know who's like our people attending our contests, because sometimes like people from all over the world are allowed to join Caddis contests. So we just want to make sure that it's our people doing the contest problems. The links are all here. So today's agenda, firstly, we're going to be going over recursion and tabulation. So it's going to be a pretty brief introduction to both, and maybe just touching up some concepts that you may have learned in CS classes. And then we're going to go over an example called tiling Dominos. So there's going to be a problem that's not on Caddis. So we'll just show you the example and then give you the code solution for it. And followed by that, we will have two problems that you'll be able to solve on Caddis. And these will also just be going over the solutions at the end. All right, let's get into it. So first up, we have the topic of recursion. So in order to discuss recursion, we need to talk about recurrence relations. And what those are is that these are equations that recursively define a sequence where each current term is a function of the previous terms. And in recursion, we require initial values slash base cases. And there'll be some examples on this in the upcoming slides. And recursion is a method of solving a problem where the solution depends on solutions to subproblems. And if you've done similar problems in CS classes, basically these are functions that call themselves within their own code. And if you haven't seen one yet, don't worry, we will show some recursion examples in the next few slides. So now, what is dynamic programming, also known as DP? Basically, DP is a technique for solving an optimization problem by breaking it down into simpler subproblems. Here, we utilize the fact that the optimal solution to the overall problem depends on the optimal solution to the subproblems. And it's also an optimization over plain recursion, because usually in recursion, there are some times when we call the same function over and over again with the same inputs. But with DP, we can actually just calculate subproblems once and then store the values so that they can be used in future function calls. And we'll be showing you examples for DP as well. So here are some example recurrence relations. A very simple one is the factorial, which is the sequence 1, 1, 2, 6, 24, 120, and so on and so forth. So what factorial is defined, it's written as n exclamation mark. And so for the base case, we have 0 factorial is equal to 1. And for all future terms, we have the recurrence relation where n factorial is equal to n times the factorial of the previous number. So, sorry, for example, 6 factorial is equal to 6 times 5 factorial, and so on. And another simple recurrence relation is the Fibonacci sequence. And for this, the base case is f sub 0 equals 0 and f sub 1 equals 1. And for all of the following terms, the recurrence relation is that each term is the sum of the previous 2 terms. So for example, 8 equals 3 plus 5, etc., etc. So now let's look at a code example for the Fibonacci sequence. So here is the function fib. And in this function, we're going to calculate the Fibonacci sequence, or the nth term of the Fibonacci sequence. So the base cases are n equals 0, or you can say n is less than or equal to 0, and n equals 1. So basically, we return f sub 0 here and f sub 1 here. Then for all other values of n, we're going to return the sum of the previous 2 terms of the sequence, which is why we say fib of the previous term plus fib of the term prior to the previous term. And so here you see that we're calling the same function within its own code, which is why it's called recursion. And so why should we use dynamic programming? Well, if you look at this graph or this diagram of the Fibonacci numbers, we see that in order to calculate the sixth Fibonacci number, we need to calculate the 5th and the 4th. And for each of these, we need to call like even smaller. We need to call fib with even smaller numbers. But see that here, the time complexity is exponential because we need to do the same calls over and over again for each subproblem. So for example, here, Fibonacci sequence, the second term, we're looking for that like 5 times. And that's going to take up a lot of time, and we kind of want to save time with this. So that's why we use DP to optimize such a problem solution. So that's where tabulation comes in. Tabulation is basically a technique for DP that will help us to optimize the code. So in tabulation, instead of thinking recursively, we start from the bottom up to find, for example, in this example, we find the nth Fibonacci number. So we start with the base cases, which is fib of 0 equals 0 and fib of 1 equals 1. We start from there and we calculate the second number, the third Fibonacci number, the fourth Fibonacci number, and so on. So notice that here, since we're starting from the very bottom, we actually only need to calculate each number once. And at each iteration, we're going to store the value so that we don't need to call the function again. We can simply use the value that we have already stored. So this is going to save a lot of time. So yeah, here's the example of Fibonacci with tabulation. So we're going to first have a vector or some data structure to store the values of the function calls. And we start with the base cases. So f of 0 equals 0 and f of 1 equals 1. And then starting from f of 2, we're going to start using the recurrence relation here. And we're just going to store each value in the vector. And at the very end, we just return f of n, which is the number that that is the inputted value for the function. So this is going to be very fast compared to the recursive function, especially with large values of n. So I'm also going to just bring up memoization as well. So basically, tabulation and memoization are both methods to store values of subproblems. But the difference is that tabulation is from bottom up and memoization is from top down. So here's the example. So here's the example of us calculating the factorial. So we start from the base case and we build up the vector from the 0th term to the first term to the second term and so on. But for memoization, we're given the nth, we're also given the nth number as the input, but we check the array if this number has already been calculated. And if not, then we calculate it, and otherwise we just return the number. So we start from whatever numbers inputted, and then we go down one by one until we find like the number that's like calculated, and then we start returning the values. So here, notice that it's still kind of recursive because we still have to call the function within its own code. But it's faster than recursion because we only need to like return the value in the vector. And so here comes the question. How can we recognize if a problem can be solved using in order to avoid these repeated calculations, we can just store them in an array so that we only need to calculate them once only. So in summary, DP is an optimization technique. It breaks the main problem down into smaller and simpler subproblems. It solves each subproblem just once, stores the solutions to the subproblems to avoid repeated calculations, and this is going to save time. Moreover, once you identify a DP problem, you should try to do the following. You need to identify the variables / parameters that are given to the function, i.e. which values are changed at each call / each iteration. Also, very importantly, you need to identify and express the recurrence relation in the problem. And this is usually the hardest part. Usually the current element is related to the previous elements that your program has seen. So in the Fibonacci example, each term is the sum of the previous two terms. And yeah, so now we're going to go over the first example problem. It's called tiling dominoes, and here is, I guess, a visual of the problem. So we're given a 2x(n) board, and here this one is 2x6. And a domino is basically like a 2x1 slab. It's a combination of like 2 tiles. And we want to find how many ways we can tile this board with dominoes. And yeah, so if anyone has any guesses already, feel free to like unmute yourselves or drop your guesses in the chat. But we'll go over like some base cases next. So first, let's start with a 2x1 board. Yeah, so this board, you know, there's only one way to tile it because, I mean, a domino is just 2x1, so you can't really tile it any other way. And that's pretty obvious, right? And then, yeah, we're going to go to the 2x2 case next. Yeah, so does anyone want to tell me how many ways you can tile this board?
There's 2 ways.
Yep, exactly. Yeah, someone said 4, but actually, let me just show the graphics and then you will see. There are only 2 ways to fill this board because remember, the dominoes are 2x1, right? So there's only, you can only place 2 tiles vertically, or you can place 2 tiles horizontally. And there's not really another way to do this. So for this case, there's only 2 ways to fill this board. And for the next case, n equals 3, there are 3 ways to tile this board. What we can do is place 3 tiles vertically, or 1 tile vertically and 2 horizontally, or 2 horizontally followed by 1 vertically. And lastly, this is the last example. We're going to have n equals 4, and there are 5 ways to tile this. So you can just take a look at these boards and maybe think about how to find a pattern between each size of a board with the previous boards. And yeah, if you happen to notice a pattern, feel free to unmute yourselves or type it in the chat. I'll give you guys a few moments to think about a pattern. Okay, let's take a look at how we can tile these boards. So how do we find the recurrence relation for this? We need to reduce the problem into a smaller case of the same problem. And so first, let's just suppose that we place 1 domino vertically on a 2 by n board. And so here's the board, and it's going to look like this, right? And what this means is that now we only need to tile a 2 times 2 by n minus 1 board, right? Because we can just ignore this part. We can just look at like the part that hasn't been filled. And there's another way to tile it, is that we place 1 domino horizontally on a 2 by n board. And it's going to look like this. But sorry, for this case, we're kind of forced to place another one because, like, if we look at this, we don't have a complete 2 by n board anymore. So what we have to do is we're forced to like put another one horizontally down so that we're left with a perfect 2 by n board here. And in this case, now we just need to tile a 2 times 2 by n minus 2 board. Yeah, so let's call the number of ways to tile a 2 by n board by tilings of n. And there are just two types of subproblems. One type is where you place one tile vertically, and in that case, you only need to fill a 2 times n by n minus 1 board. And in the other case, you have to place down 2 tiles horizontally, and here you have to fill a 2 by n minus 2 board. Yeah, so this is basically tilings of n minus 1, and this is tilings of n minus 2. So does anyone want to guess like the exact recurrence relation based on this picture?
So tilings of n is equal to tilings of n minus 1 plus tilings of n minus 2.
Yep, exactly. That is correct. So You're totally right. Tilings of n is equal to tilings of n-1 plus tilings of n-2. And here's like a table with all of the number of ways to tile for each value of n. And if you noticed here, it looks pretty much like the Fibonacci numbers, except the only difference is that the base cases are f(1) equals 1 and f(2) equals 2 of the previous two terms. So yeah, this is going to be pretty easy to code up the solution to. Here's the code with plain recursion. Notice that it just looks like the Fibonacci one. If n equals 1 or n equals 2, these are the base cases, we just return n. And otherwise, for all larger numbers or all larger values of n, we're just going to return the sum of the previous two terms. And yeah, so this is the recurrence relation. And we know we can optimize this with dynamic programming. So what we do here is have a vector or an array or some kind of data structure. And we're just going to fill up the first two values with the base cases. And then starting from the third value, we're going to just do the recurrence relation, summing up the previous two terms. At the very end, we return the nth term. Great. And yeah, so now it's time for our first caddis problem, which is called tritiling. And here's the link to the examples contest. You can just click on it and then join with the caddis account that you've created. And also one thing to note is that you're not expected to solve all the example problems perfectly because they're meant to be instructive and they're just here to help you prepare for the weekly contest and just to like teach you new concepts. And so don't worry if you're not able to solve the problem within a certain period of time. And yeah, we're just here to help you. So have a few minutes to look at the problem and then Raya will go over it.
Awesome. Hey guys. Okay, cool. Hopefully you had a chance to like look over the problem, think about how you might start solving it. I'm Raya. I'm going to go into how you would solve this problem. Can you hear me, by the way?
Yes.
Yes. Okay, cool. Just checking. Thank you. All right. So tritiling. If you approach this problem, not even knowing it was like DP or anything like that, where would you start? Well, a good place to start is just trying some things out. So let's do that. So starting with a 3x1 rectangle, how many ways could you tile it using 2x1 dominoes? Immediately, you kind of run into a problem. Like, that's weird. There actually isn't really a way to cover 3 tiles using just 2x1 dominoes. The amount of squares you want to cover will always be even, but 3x1 is 3 squares, and that's odd. So, well, but I don't know. This is just the first case. For now, this is just kind of an observation, not really a pattern. So we can note that and keep going. Okay, so how many ways could you tile a 3x2 rectangle with 2x1 dominoes? I'll give you a second to think about this if anyone wants to tell me.
Two ways? Or
Did you say, I'm sorry?
3. Sorry, I said 2 originally, but I realized it's 3. Never mind.
3. Yeah, 3. That's perfect. That's a good answer too, though. Perfect. Yes. Here are the 3 different ways you can tile it. Yes. So let's keep going. Can anyone tell me how to do 3x3? I would let you answer, but probably not.
An odd number.
Yes. Perfect. 0. Because again, we went into the same problem from earlier. 3x3 means 9 squares. That's odd. So it just seems like we kind of can't tile it. And now that we've come up against this a second time, we can maybe sense that this might be something that's like significant to our problem. So we just unlock this intuition that dealing with even values of n and odd values of n might be different. So we can explore that. So to make it easier to put into mathematical terms, we'll just define a function, t of n. That's the number of ways that you can tile a rectangle of size 3 by n. So if you see, t of some value, just know it means how many ways you could tile a rectangle of size 3 by that value. So we're going to start with even tiling because that's the only thing we know for sure that we can actually tile. So let's just say that n is equal to 4. So we have a 3x4 rectangle, right? I think just starting with this, it's natural to think, at least for me, isn't this just two 3x2 rectangles side by side? So we could potentially just find all tilings by treating each rectangle as though it were an independent 3x2 rectangle, right? And kind of, that's a great idea and definitely part of the solution. But just looking at the given test cases, we can see that there are some tilings that don't work like this. Like, what about a tiling like this? We can see that these are two different 3x2 cases, and then, you know, Dominos right there crossing the line. So we kind of have two different cases. One, where we can start tiling like we're tiling a singular 3x2 block where no dominoes cross this line, and one where we can't. So now all we need to do is look at these individual cases. So first, let's just say we don't cross the line and we just tile this like we tile a 3x2, a singular 3x2 rectangle, right? Cool. So now if you put in your DP practice, because, okay, DP, I mean, this is the first workshop, but it's hard. It could be alien at first. So like, if you're not getting it immediately, don't be like mad. But if you put in your DP practice, you might recognize a recurrence relation forming. If you're still not like well-versed in what that is, that's fine. The point is that if you magically knew how many ways you could tile this rectangle of size 3 by n minus 2, or t of n minus 2, then all we need to do to find t of n is multiply t of n minus 2 by t of 2. And to make that more concrete, remember that we calculated t of 2 earlier. It's the amount of ways we could tile a rectangle of size 3 by 2, and it's 3, which means that you could tile, for each way that you can tile a rectangle of size n 3 by n minus 2, the rectangle of size n, you get 3 different variations of that. You can see that right there. So yes, our equation for this is t of n minus 2 times t of 2, when no domino crosses the line for even n. Okay, now let's look at the other case of dominoes crossing the line. So there are 3 ways where that could happen. Check these out. Let's see what happens if we try to tile the top one. So we have to put a domino here, here, and here. And now we end up with this weird structure. It's like a rectangle of size 3 by n minus 3, but the lower corner is missing, which is interesting, but we've already gotten kind of far, so let's just keep going. You can try and tile this. We'll see immediately kind of that doesn't work. You try it for yourself, you know, put a domino here. That's not going to work. But what happens if we try and tile this bottom one right here? Put a domino here and there. And again, we end up with a rectangle of size 3 by n minus 3, but this time with the upper corner missing. And that's weird and a little bit annoying, but we could possibly still make our magical DP assumption that if we somehow knew how many tilings existed for rectangles of size n minus 3 with a corner missing, we could solve this problem. So let's just put it in our solution, at least for now. So that's it. Now we've dealt with the possibilities for the even case. Adding them together for any n, t of n is equal to t of 2 times t of n minus 2 plus t of n minus 3. This is the case where, again, they don't cross the line, and this is the case where they do. And you may notice that I put t of n minus 3 instead of like 2t of n minus 3 or something. This is just because t of n minus 3 refers to all rectangles of size 3 by n minus 3 with one square missing. So that includes both rectangles with the upper corner missing and the lower corner missing in that one term, just in case you were wondering. Okay, I know that's kind of a lot, and I'm going kind of fast. This is just due to time constraints. You're not like expected to understand all of it like immediately. So I guess I'll stop here for questions really quickly, if anyone has any so far. Cool. All right. Also, feel free to like ask them later in the breakout rooms and stuff. All right, so we're halfway there. We just have to tackle how many ways can we tile the rectangles when n is odd. Alrighty, so we already know that if n's odd, we can't tile it because there'll always be a square left over. So our program will actually have to output 0 for this. But we know 2 things now. If we want to meaningfully engage with this problem in like a DP recurrence relation way, we're going to want to find some sort of way to like tile this. Also, we know we have these weird structures where we have like a rectangle with a square missing. And So how about we kill two birds with one stone and just make this into a case where there's a rectangle with a square missing and call that our odd n. Call that what happens when n is odd. I mean, that's kind of weird, kind of a jump, but it would work, maybe. So let's do that. So for tilings with odd n, that gives us two options. We remove a square from the top corner or remove a square from the bottom corner. And just to make it easier, I'm just going to call these ones upper cornerless and these ones lower cornerless rectangles. Hopefully that makes sense. So let's explore each subcase and see if we can find a pattern. So looking at the upper cornerless rectangles, let's say we wanted to place one tile in here, starting at the bottom right. How many ways could we place that? If anyone wants to. I'll just say we could place it either vertically or horizontally, right? So that gives us two options. Again, we have two subcases. What happens if we place it horizontally? Well, this happens. We're forced to put a domino here, we're forced to put a domino here, and suddenly we end up with a upper cornerless rectangle of size, what is this, n minus 2. This is another recursive relation forming. So if you magically knew the amount of ways you could solve this, you could solve the whole thing. You'd know that they're equal because when, like, notice how this we were forced kind of to put this domino here after that. So every tiling here, you just tack on these three and you got the same thing. So keep that in your brain and we'll move on. So what if instead we place the first tile vertically? Well, this happens. And suddenly we've reduced our upper cornerless rectangle to a full rectangle of size 3 by n minus 1. So again, a recurrence relation. If we knew how to solve that one, then we could solve the whole thing and just tack on this domino right here. Perfect. So to recap what we just discovered, for upper cornerless rectangles, the total amount of ways we could tile it would be the amount of ways we could tile the rectangle of size n minus 1, which is t of n minus 1, plus the amount of ways we could tile an upper cornerless rectangle of size n minus 2, which is t of n minus 2. Perfect. So we're almost there. And now we just want to move on to the case where we could, with the lower cornerless rectangles. We're lazy, at least I'm lazy, and I don't want to like do all that work again. So we can just make the realization that this is literally the exact same thing at the mirror version. So it'll be almost the same thing except t of n minus 2 for lower cornerless rectangles. And remember, these t of n minus 2 with upper cornerless rectangles plus bottom cornerless rectangles, that's just t of n minus 2, which is great. So now we have a whole term. So when we combine this, we can get t of n is equal to 2tn minus 1 plus tn minus 2. And that is it. So the total ways to tile it when n is odd is right here, and the total ways to tile it when n is even is right here. All we have to do is code it up. And then put it in code. So Rishi wrote this. He's going to do advanced dynamic programming next week. So stay tuned for that. But I'll just explain this really quickly. If you look at the input, we need a table of size 31 because it's from 0 to 30 inclusive, and that's 31 numbers. And so we have our base cases. It does include a rectangle of size 3 by 0. I don't know why, but just put that in there. It's a base case. And then the base cases we came up with. And then literally you just go through the for loop of the equations that we came up with. So if it's even, do this. If it's odd, do that. And then if it's even, see out what we came up with. And if it's odd, see out 0. And that is it. Hopefully that made sense. It wasn't too fast or too slow. But if you have any more questions about it, please come see me or any of the other officers in breakout rooms later. Get back to lending. If I can.
All right. So yeah, thank you, Raya, for that really awesome presentation on tritiling. Now we're just gonna move ahead to problem B, which is knapsack. And again, you can find the link right here. So yeah, knapsack is a really classic problem, I think, and it might come up maybe on like interviews and stuff. So it's pretty good to know a problem like this. Yeah, so feel free to just go ahead and read the problem for a few minutes, and then we'll get into the explanation. All right. Yeah, so we didn't expect you to like definitely not solve the problem during these few minutes. So we're just gonna try to help you like understand the problem better and to give you a solution so that you'll know how to code it up later. Yeah, let's get into it. So we're given like a bunch of numbers in the input output, and they're separated by test cases. So here we have test case 1, which is this, followed by this output. And here's test case 2 with this output. And yeah, so here's going to be the idea of basically how to approach the problem. So we are given the weights and values of some objects, and our goal is to select the objects that give us the maximum total value without exceeding our weight capacity. And for each problem, you only have 2 choices. You can either take the whole thing or reject it. And notice that we can't take like a partial item or get a partial value. We either take it or leave it. And yeah, so here's a knapsack, and here are some objects that you might be able to put into your knapsack. Okay, so I think test case 1, it was maybe not the best example to like test out the DP solution. So we're just going to be discussing the second test case. And here, here's the again the input, and here's the output. And in this problem, we're given that C is 6 and N is 4, which means that we have a weight capacity of a total of 6, and there are 4 objects to choose from. And yeah, do you think you guys could identify the subproblems? Yeah, for this problem, it might be a little bit difficult to see the subproblems first, but just one thing to note is that for DP, sometimes there's like multiple variables that you need to keep track of. So in the tritiling and domino tiling problem, we only needed to keep track of one variable, which is like N, right? Like the size, the width of the board. And in like the Fibonacci sequence, we only needed to keep track of like the nth element. But for some DP problems, we need more variables that change at each iteration. So it might be a little bit difficult to identify the subproblems first, but I hope that this following explanation will help you understand it a little better. So yeah, how do we define a subproblem for this particular problem? Well, first, let's just, I guess, label our parameters. So we can label the sequences of items as 1, 2, 3, and so on, up to N, which is like the first item, the second item, and so on. And we're given a total weight capacity of C. So for this, a subproblem could be to find the solution for the subsequence 1 through K, and K is smaller than N. And also for a subset of the weight capacity C, which is also smaller than the big C that we're given. So basically, we're trying to find the solution to a smaller set of given objects and a smaller knapsack. And here, we're going to ignore capacities that are larger than the given capacity, since there's no point of exceeding it because we're not able to like put in all items in the overall knapsack, right? And similarly, we're going to ignore values of K that's greater than N because we're only given so many items. So we're only going to care about values of K and little c that are less than N and big C respectively. And yeah, so here is going to be how we're going to define the recurrence relation. So first, we need to think about what we can do with each item. we can either keep it entirely or discard it. And so let's consider an object with weight W and value V. If we keep it, then we're going to add its weight to our current sum of weights, and we're also going to add its value to our current value. So this was what's going to happen. And on the other hand, if we discard the object, then we don't change anything. The sum of weights remains the same, and so does our total value. What we want to know now is, when should we keep an object or discard it? So the first very obvious case is that if we can't fit the object in our knapsack, then we have to discard it. And here what it means is that the weight of the object plus how much we already have is greater than the given capacity. But if we can keep it in the knapsack, we have to choose basically. So we need to check if it gives us the best value. So like, for example, if you have an object or if you have two objects, both with weight 5, and one is like worth $100 and the other is worth $10, what you want to do is like keep the one that's more expensive, right? Because we want to maximize our overall value. So if an object gives the best value, we're going to keep it. Otherwise, we will discard it. So now let's consider the subproblems. So let's just think about the kth object and give it a weight W and a value V. And at each subproblem, we're going to compare the following values to find the optimal choice. And here, like, the subproblem just means we're considering a subset of the items and a subset of the weight capacity. So we're going to compare these two values. The first one is the maximum value up to the previous object and up to the current weight capacity. The second value that we're going to compare is the maximum value up to the previous object and up to the weight capacity C minus W, plus the value of our current object. So in this case, why do we want capacity up to C minus W only? It's because currently we're just considering C as the max capacity. And if we want to add this object, we're going to add V to the weight capacity, right? Or sorry, we're going to have to add weight W to the max capacity. So we don't want to exceed the capacity C. So that's why we only consider the maximum value up to the weight capacity C minus W. And it might be a lot to take in right now. So just think about this while we go over the next, or go over the example. So yeah, so based on what we said in the previous slide, we can pretty much already define the recurrence relation. So let's just denote B of K comma C as the best value at the kth object and up to the weight capacity C. Remember that K is just a subset of N, and little c is just a subset of big C. And here the kth object has weight W and value V. So the recurrence relation is given as follows. So in the first case, the best value at this object and weight capacity is the same as the best value at the previous object and the same weight capacity. So what this means is that we're just discarding the object because the current object is not going to affect our best value. So this happens when the weight is greater than the capacity. In the second case, it's going to be the max of the best weight up to the previous object versus the best weight up to the previous object and C minus W as the capacity plus the value of our current object. And yeah, so here's what each term means, just to remind you guys again. And we also need to remember that there are base cases for this problem too. And here, the base cases are best value is 0 if k is 0 or c is 0. So what this means is that if there are no objects, then obviously our best value is 0. And if the capacity is equal to 0, then obviously we also can't put any objects into our knapsack. So that's why the best value is 0 for each of those cases. And now let's take a look at the sample input and output. So this is the test case number 2, where we were given that the max capacity is 6, and there are 4 objects. And I'm just going to label each object with k as the variable. And here are the values and weights of each object. So here's the first, or one of the subproblems. So we only consider the first item, only one item out of all of them that were given. And for this, we're going to consider different subproblems depending on the capacity. So we can consider capacity of 1, capacity of 2, and so on, up to capacity of 6, which is the max that we're given. So when we're considering this first item, there are 6 subproblems. And now we can also consider if we're given 2 objects. And once again, we're going to consider capacities 1 up to 6. Similarly, for 3 items and 4 items, each time we're just going to consider the first through 6 values of the capacity. These are all the subproblems that we're going to consider. So yeah. And so now let's look at the case where we only think about the first item. So it's pretty obvious at first that for capacities 1 through 3, the best value is going to be 0, because this first item, it has weight 4. So we're not going to be able to fit it into a bag of capacity 1 or 2 or 3. But starting with capacity 4, we can fit it into our knapsack. So here, at B1, 4, it's going to be 5 as the best value. And likewise for B of 1, 5 and B of 1, 6, the best value will also be 5. And this is because there's only one item to choose from, so it doesn't really change. Next up, we're going to look at the case where we consider the first 2 elements. And once again, for the first 2 weight capacities, it's going to be 0 because we can't fit any of these items into our bag. But starting at capacity 3, we can fit the second element into our knapsack. So that's why it's going to be 4. The best value is going to be 4 because this item has value 4. And now, starting here, we're going to think about like which item to put into our knapsack. So at capacity 4, we're able to fit both this item and this item. But because the first item has a better value, we're going to put that into our knapsack. So that's why at this case, the best value is 5. And for the remaining weight capacities at k equals 2, it will be 5 because we can only fit one item given their weights. So it's going to be 5 for the rest here. Now let's look at the case where we consider 3 items. Same deal for the top couple of weight capacities. And now when it reaches capacity 3, we can, again, either select this item or this item. And because item 2 has a better value, we're going to select this. And so the best value is going to be 4. And once again, pretty much the same deal. Select the best item that we can fit into our bag at the current capacity. And now the interesting part comes when we reach capacity of 5 at the third, when we're considering all the 3 first objects. So here, we're going to look at, again, what's the best on this row. We're going to compare like 5 because remember, looking at this this recurrence relation, we're going to look at the same capacity, but considering only the first two items. So we're going to look at this object, or sorry, we're going to look at this subproblem specifically versus b of k minus 1 of c minus w plus v. So here again is in this column, but c minus w here is 5 minus 2, which is 3. So we're going to compare this with this, and again, we have to also add the value of the current item. So we're basically thinking of 4 plus 3 versus 5. And here, because 4 plus 3 is greater than 5, we're going to go with 4 plus 3, which is 7. And same deal here, we're comparing this with this, and we get that b of 3 comma 6 is going to be 8. And we just go through the algorithm over and over again for the remaining column, and at the very end, we get 9. And indeed, if you probably did this problem in your head, you will find that the best value is indeed 9. We're just going to pick this item, and this item, and their values add up to 9. So now that we've used this algorithm, we're going to actually answer the question. So the problem statement, it asks us to print out the number of objects that we selected as well as their indices. But in order to do that, we needed to calculate like the best value to find out which objects to select. So now we're going to go through this array and find out which objects we actually selected. And how we're going to do this is just start backtracking. So what we're going to do here is we should start at the very last element in the array and go from top down to find the indices of the items that we selected. So remember the formula that we had, which was like this part specifically, where we basically compare the item in the previous row with, oh, okay, sorry, here it's, I did it in columns, but let's just say we did it in columns, and we're gonna compare the item in the previous column versus v plus the item in another item in the previous column, but in a lower, or in a smaller value, or how do I say this, in a higher row. So I kind of did this array kind of like switched the columns and the rows, but I think you get the idea. So this row, this is considered a row in like an actual visual representation of an array, but here I just did it in columns. So yeah, so we compared these two values. So what we're gonna do now is once again compare like the values that we're given in the overall table. And so first, we're going to compare b of k comma c with b of k minus 1 comma c. And if they're not equal, then the kth item must have been chosen, because what this means is that since this value is different from this value, it means that we must have selected this item, because we changed the best value at this column. And so when we compare 8 with 9, we notice that they're different, which means that the fourth item must have been chosen. And this is from the subproblem k equals 4, c equals 6. And next, we're going to look at a smaller subproblem, which is k equals 3 and c equals 5. And why is this? Well, that's because we know that we've selected the fourth item. So now we're going to look at, the subproblem with 3 items instead. And here we're considering c equals 5. And this is talking about the capacity of the subproblem. So here we know that the fourth item has a weight of 1. So we have to subtract that because we're subtracting one item now. So this is going to be 6 minus 1, which is 5. So we're going to have to look at b of 3 comma 5 now. And once again, we're going to compare B of K comma C with B of K minus 1 comma C. And again, they're not equal, so we know that the third item must have been chosen because the best value changed when we considered the third item in this weight capacity. So we're going to add that to our list of selected items. And in the same fashion, go to K equals 2, K equals 2, C equals 3. And again, they're different, so we know the second item must have been chosen. And so in the same fashion, we go to K equals 1, C equals 0. And so now you know that like we're subtracting 3 from the weight, so that's why C is 0 here, because 3 minus 3 is 0. And lastly, we're going to look at this entry. And notice that here, the subproblem is at a capacity of 0 and the best value is 0. So this means that no items could have been selected up to here because there's like no value here and there's no capacity either. So we can't have selected any values, we can't have selected any items up to here. So we just end the search. And this means that we must have found all the chosen elements already. And they're all listed right here. And so in code, what we do is just keep this number of selected items, keep all the indices of all the selected items in an array, and then we can print them in reverse order. So yeah, here's the code solution to this problem. First, we just do the input, which is pretty simple. We're given C and N, and we put them into arrays representing the values and weights. And then here's the DP array. This is where we do the tabulation, and it's going to be of size n+1 by C+1. Then here we just follow the recurrence relation. So we iterate on the number of items in the outer loop and on the weight capacity in the inner loop. And if we can't fit the current object into our knapsack, then we discard it, which means that we just keep the best value up to the previous element and the same weight capacity. But if we can fit the object, then we just do the recurrence relation where we find the best value based on the subproblems. And this is the same equation as on the previous slides. And yeah. And here's the part where we actually do the backtracking and print out the indices of the elements that we selected. So we're going to have two variables. One's called best to represent the current best value, and C to represent the subset of the overall capacity. And we're going to start from the very last element and work our way down. So if the current best value is not equal to our best value, then the object must have been included. So we add its index to the array of indices, and then we're going to subtract the values and weights of the item we're currently iterating on, and then that way we can figure out which item to go to next. And we just keep repeating until we reach the end, until either K is 0 or best is 0. And then at the very end, we just print out the number of items picked, and we start printing out the indices from back to front. And that is all. So that's all for the solution to this problem. I think it's definitely a harder problem, and it's not very easy to understand at first. So I would recommend just like maybe reading over the slides or just thinking about it a bit more to figure out what the recurrence relation means and why the backtracking algorithm works this way. And I hope that eventually you'll just understand how this solution works. And that is all. You can click on this link. And there's some problems. So the first problem on the contest, by the way, it's like an ad hoc problem. So it's not actually DP. And it's just for fun. And then the remaining 4 problems are DP, and it kind of increases in difficulty one after the other. Yeah. Thank you.